So up to the last class, what we have done is basically we have made an inverted index, right? So we discussed on the making the inverted index, specifically the dictionary, which is basically all the terms in the vocabulary. And for each of the terms, there will be a posting list. So in the up to the last class, we have discussed on making this kind of an inverted index from a raw text. So today's agenda will be how to actually compress these two data structures. As we have seen in the last class, there can be issues with keeping them in the primary memory. Note that again, I'm giving you a recap that every operation on some data can be computed only if the data is in the primary memory, and we know the primary memory is limited. In the primary memory, a major portion will be occupied by the operating system. There will be some other applications such as say Internet Explorer, some other software or regular service that are running. Together with that, if you start making indexing process, the primary memory might be overflowing. In that case, we have discussed the swapping will be applied, but of course, accessing the disk is actually time consuming. So we need to overcome those kind of a situation. So one way of reducing the space consumption is by using compression. So in today's discussion, we will be discussing how to compress the dictionary as well as how to compress the posting lists. Together with that, we will be having another discussion on understanding whether there is any statistical property of the terms in the collection or not. Is there some kind of a behavior, statistical behavior that we can observe or that we can actually predict? These three things are the agenda of today's class. So first, let me give you the general impression on the necessity of compression. So by compression, we will be given a data. Any type of data can be actually compressed. So if the data is of say txt or simple text file in the form, if the data is in the form of text file, it can actually be compressed to a much less size if the size of the txt file is m. And if I compress it to make it say some kind of say to some .zip, and if the size is n, we know m will be much larger than n. That is, the zipped file, the size of the zip file will be much smaller than m. This might not be the case if the file type is of say music file having an extension of .mp3, or a video file, let's say mp4, or other video files like mkv or avi or something similar. For them, this compression is not actually that much helpful. In general, compression actually helps us to reduce the space consumption. In turn, it saves us some money. Also, if we compress some data, we can actually and if we keep the compressed data in the hard disk, and if we use that data to compute something in the RAM, it will be actually, if the data is, so if I read this data, which is having size m, as compared to if I read this data as compared to the size which is n, which is less than m, the amount of data that needs to be transferred from the hard disk to the RAM will be actually reduced, which will actually increase the speed of the program. And increased speed of transferring the data from disk to memory, again, it will be increasing the speed. Again, if in the RAM, instead of keeping the raw data, if we keep the zipped data, or if we develop some kind of an application which can actually work on the zip data or on the compressed data, it will actually be taking less time in the primary memory as well. That will be actually increasing the speed. Why? Because it will be reducing the possibility of swapping. Again, what is swapping? If the primary memory is full, some portion of the primary memory is swapped into the hard disk, into the swap space of the hard disk, to free up some space in the primary memory for basically accessing or for basically computing with some data. Now, if we keep the zipped data or the compressed data, the overflow of this primary memory can be reduced. And in general, why should we be using compression in case of information retrieval? So, as we have seen in the information retrieval, there are two major things in an index, which is basically the dictionary and the posting lists. So the dictionary is basically containing all the terms in the vocabulary. So if we compress it, it will be taking a small amount of memory. And if you remember, this dictionary should be in the random access memory or in the primary memory all the time during the retrieval, because in the random access memory, the dictionary needs to be checked every time one query is submitted. So if if this is a dictionary which is kept in the RAM, the dictionary is basically the term and some, let's say it's only the pointer, the term, the posting list pointer, and so on. When a query is submitted into the system, so for that query, for each of the term of that query, we need to look up this dictionary to get the corresponding posting list. So we need to keep this dictionary every time in the random access memory. And if we can actually compress the dictionary, it will be taking less time in the less space in the random access memory. Next is compression of the posting lists or postings. It will be basically postings are much larger than the dictionary. Why? Because if matrix that we have drawn earlier, by each of the row, if we place the terms, like T1, say Tm, m number of terms, and D1, D2, up to say dn number of documents. So while performing so this is essentially, from the point of view of visually realizing the data, this is actually similar to kind of an inverted index. Why? Because in the inverted index, we are storing this term and the documents where they are actually present in. So in the term incidence matrix, as we have seen, there will be zeros and ones based on the presence or absence. If it is absent, if the term is absent, it will be 0. If the term is present, it will be basically 1. So in case of inverted index, we are only storing this presence, right? We are only storing by this posting list, we are only storing the presence of the term. So the definition of the posting or posting list from the incidence matrix can be defined as this. So the posting list of a term is basically the term incidence vector, as we have discussed earlier, the term incidence vector without the zeros, right? And in the term incidence vector, we are storing the zeros and ones here instead of zeros, so we will not be storing the zeros, and instead of the ones, we will be storing the corresponding doc ID, right? Now, so as you can understand, the number of terms will be much larger than the number of documents, and for each document there will be basically, I mean, so basically in the dictionary, now again if we talk this, I mean if we view this from the inverted index point of view, this is basically the dictionary, this is basically the dictionary, and the entire thing, entire matrix without these zeros, is basically the posting lists. Now we can understand that posting list is much larger than a dictionary. So if we can compress this, it will be actually reducing the disk space, because essentially this entire posting list will not be, I mean, we will not be able to save it in the primary memory. So we need to store it in the secondary memory. And on the fly, whenever there is a need, whenever there is a query to extract certain posting list, we will be accessing the hard disk at that time, not always. Again, I am repeating, for a large collection, I mean, of course, we need to keep this dictionary in the memory, in the random access memory. But these posting lists can not always be kept in the random access memory, because it is too large to be fit inside a random access memory. That's why we need to keep it in the secondary memory, that is hard disk. But note that there are pointers. So in this dictionary, what we are storing the term, the document frequency, and some pointer, right? What is this pointer? Now I hope you can understand. This is basically the address to the hard disk, where exactly this term is stored. So this is basically the address in the hard disk, in the secondary memory, right? So we need to have a compression of the posting lists to reduce the disk space needed, basically the secondary memory space needed to actually, I mean, this will be actually helpful during the retrieval as well, in which case we can actually, I mean, this kind of a compression can results in a small amount of memory, a small amount of information being transferred from the hard disk to the RAM, right? Now, large-scale search engine such as Google or Bing, it actually keeps certain part of the posting lists in the primary memory as well. Now, can you guess what type of, I mean, for which terms this kind of posting lists are stored in the primary memory? Can you just make a blind guess? Anyone? So I'm saying that in general, posting lists are stored in the secondary memory. But for a large scale search engine, they keep certain part of the posting lists into the primary memory. This is primary memory. By memory, I am referring to primary memory, that is RAM, to access those documents quickly. Now, can someone guess what type of document should be kept in the random access memory, in the primary memory? It is basically, at that point of time, the documents which are trending, or the documents which are basically very popularly accessed by the user. Those documents are stored in the primary memory by the large-scale search engines. So in today's lecture, I will be discussing certain techniques to actually do this kind of a compression. So in general, very broadly, we can actually divide the compression technique in two different categories. One is lossy and another is lossless. So lossy compression is the scheme, or is the operation where we are discarding some information while compressing the data, such as downcasing, stopword removal, or stemming. So this we have already actually used while processing the data, right? Before making the data, before making the inverted index, we were actually doing something like downcasing, stopword removal, with some advantages as well. But these are also a little bit of problematic, because we are actually losing some certain information by doing this kind of a processing. This number elimination is a technique uh, taken by or followed by some search engines, not actually practical search engines, but some restricted search engines, where we actually discard any words which are containing any number. So this is not actually true for for large scale search engines such as Google or Bing, but this is a very lame approach taken by certain can be taken by certain search engines. But again, this is a lossy compression. For the lossless compression, this is the technique that the index compression techniques follow, where all the informations will be stored. But note that we will, although this is actually lossy, we will be actually doing something. We will be actually doing all these steps while making the index.